Hello class, this week we're going to be picking up where we left off talking about one sample z-test. We're going to add on what's called a one sample t-test. So just a quick review of our z-test. Last week we talked about that's when you wanted to basically compare a sample mean to a population to see if that sample mean came from that population. And to do that you need to know your sample mean, your population mean, and the standard deviation of your population, and your sample size, giving our formula we had here. However, in some cases we don't know the standard deviation of the population, but we know the mean of the population. Does that mean we can't do this test? Well, it's a little bit more complicated than that. Basically, we can do this test, we can do this z-test still. We would just be using an estimate of the standard deviation of the population, which would be the standard deviation of the sample. So essentially the only difference would be our formula would look like this: z equals x sample mean minus population mean over the standard error, where the standard error equals the standard deviation of the sample divided by the square root of n. And you would basically just calculate everything in this the exact same way as you would with the traditional z-test when you know the sample or the standard deviation of the population. The big difference here again is that you're dividing by the standard deviation of the sample here. However, you can only use this formula if you have a large population. So basically you would calculate that almost the same way, but you can only use this with a population that's large. And generally that's set at, our book that we're using this semester says a sample of 100, and you can use this alternate formula. That's based on something called the central limits theorem that we'll talk about in our next video. Some books actually set that sample size at 30, so actually our book's just being more conservative with that sample size of 100. But all you need to know, we'll go with 30 for this class just because that's more commonly the standard. If you have a sample below 30, you can't use this modified z-test. Instead, you use what's called a one sample t-test, which is almost the exact same formula. The only major difference here is that you can see formula pretty much looks exactly the same. The only major difference is when you're determining your alpha level, or sorry, not your alpha level. When you're determining your critical value using your alpha level, you actually use a different table to figure that out. And there's a few pieces of information we need to know in order to find that information on it. Essentially what we'd be using is a t-table, because we're now doing this one sample t-test, and it's a little bit different than the z-table we used with the z-test. So I'll show you guys both of those and show you how to use them. But the big difference here with the t-test versus a one sample z-test is that we're using that t-distribution table to get that critical value. And then also, before we can do that, we have to know the degrees of freedom of our sample, which is basically just n minus 1, your sample size minus 1 for this. Just a little bit more about degrees of freedom. The definition of it is basically the number of independent pieces of information minus the number of parameters, which would be, for example, the mean here. So the things we're trying to examine. And so in most cases, it's degrees of freedom, you're going to have n minus 1 in most cases. So if we had a sample of 44, our degrees of freedom would be 43. Pretty simple to figure out. Alright, but now let's compare our t-table versus our d-table. So comparing a t-table versus a z-table, let's pull up the z-table that we used from last week. Again, this is different than the one in your book, because this is the one I'll be giving you guys for your test. You can use either one, just the way you use them is slightly different. But this one's pretty simple to figure out. You just figure out, okay, what's the critical value you want? So let's say that we wanted a critical value of 0.05. Then you would also want to know again what tailed test you would need. If it's a one-tailed test, then you would just go, okay, 0.05, let's find the closest thing to that down here. Let's say this 0.0505 is going to be pretty close. Sorry. So we go over 1.6 and up. 1.64 would basically be our cutoff value for that, our critical value. But if we're doing a two-tailed test, we'd basically cut that 0.05 in half, giving us 0.025, and then we would just come down and look for 0.025 on here. So we get 1.96. So that should all be a review. But again, you're looking at what's the critical value you want, and then you go over to the sides to find your actual, you're looking for the alpha level you're setting, and then you go over to the sides to find the actual critical value that you'll compare the results of your test to. Now, t-table is a little bit different in its setup. With it, you need to know the degrees of freedom. So for the t-table, I'll show you guys here. I'll pull one up online, but it's basically the same setup as the one that's in your guys' book. If you look at the following table, you can see the t-table, again, already talked about we need to know degrees of freedom. And that's why we need to know it, because when you look at the t-table, you actually, the critical value you get is dependent on your degrees of freedom. And then we also need to know, again, just the significance value that we want to set. So if we want to set a value of, it's pretty easy. So the t-test, or the t-table is actually easier to use. If you wanted to set a value of 0.05 for a one-tailed test, you'd come down in this column and then find your degrees of freedom. So let's say we had a sample of 15, our degrees of freedom would be 14, and then if we were doing a 0.05 one-tailed test, we would just go over and say, okay, our cutoff value is 1.761. Likewise, if you're doing a 0.05 two-tailed test, it might be 2.145. So pretty easy to use. On the test, you guys will have to basically be able to look up stuff for both of it, using both these tables, the z-table and the t-table. But let's go through now and come back and talk about this. What are some of the things? Again, you just need to know, are you going to do a one or two-tailed test? You need to know the alpha level you want to set, and you need to know those degrees of freedom. If you have all that information, you can find the critical value that you're looking for. And if you recall, the critical value is what we use to evaluate the null hypothesis in that fifth step of the hypothesis test. Okay, but let's, as usual, this will probably make a bit more sense with an example. So let's use the following example problem. Let's say that we're a researcher and we want to see if taking a particular GRE prep course actually prepares people for the GRE by letting them perform better than the general population of GRE test takers. If you don't know, the GRE is basically an exam that you have to take to get into most grad schools. Let's say that we have the following information. We know that the national average on the GRE is 500. Let's say from the sample of, let's say we have 21 people in a GRE prep course, and we want to see how they compare to this general population, and we find that they have a mean of 575 and a standard deviation of 50. So first thing I want to ask here is, how do we know that we're going to use a t-test here? So take a second, try to figure that out, and then I'll come back and answer it. You may want to pause the video to give yourself some time to think about it. Alright, well, the reason we're using a t-test here again is because we have the population's mean, but we don't have the standard deviation of the population. And then we could technically still use a z-test if we had a large sample size, usually considered to be above 30. Remember, your book says 100, but usually the 30s is what most authors say. But here we have a sample of 21, which is below that 30, definitely below 100. So we would argue that our sample size isn't big enough to use that z-test anymore. So we're going to be using the t-test. So first thing we're going to do is try to figure out our hypotheses. And this time around, let's say, first again, we want to see, do we want to set a one or two-tailed test? I'll come back to that. But let's look at, let's say we want to test a one-tailed test this time, because we feel that people who take the prep course are actually going to do better on the GRE than the general amount of test takers. So our null hypothesis in that case would be there is no significant difference between people who take the GRE prep course and the general population of test takers. And our research hypothesis would be, because it's one-tailed, we're hypothesizing a direction here, it would be that those who take the GRE prep course do significantly better on the GRE than the general public of test takers. if we made it a two-tailed test, you wouldn't say that they do better. You would just say that there's a difference between them and the general population. But since we decided we're going to do a one-tailed test here, we'll stick with that. Our step 2 in hypothesis testing, if you recall, is to pick a test statistic. We already know we're doing a t-test, so we'll kind of skip over this. Step 3 is finding our critical value. And remember, to figure out a critical value of a t-test, we need to know, are we going to do a one or two-tailed test, and we need to know the alpha level. Just to kind of stick with a standard alpha level, let's say our alpha level is 0.05, and we're doing a one-tailed test. So our next thing we need to do when we're doing this t-test is determine our degrees of freedom. We had a sample of 21 students, so degrees of freedom n minus 1 equals 20. So now we can use this information. If we go back and look at the table we looked at earlier, we say degrees of freedom 20 here, and we're doing a one-tailed test of 0.05, 0.05, 20, see where those cross each other, and we get our critical value, which in this case is 1.725. So you can see that's pretty easy to figure that out. So to review so far, we know that we have a critical value of 1.725. And remember that we'll be comparing that critical value to the information that we get after we actually calculate our test. So that takes us to our fourth step, actually calculating the t-test. It's very similar to how we calculated the z-test earlier in our last unit. Again, we need to know the sample mean, the sample standard deviation, the population mean, and the sample size, and we can calculate this. So first, there should actually be a bar over this, so this should actually be x bar. So x bar, sample mean, minus mu, or the population mean, divided by the standard error, where the standard error equals standard deviation divided by the square root of n. So the first thing we'll probably want to do here is get the square root of n, which that would just be getting the square root of 21, which we can see here looking at the calculator. Throw in 21, square root 4.582, let's round that to the 2 decimals, we would get 4.57. So come back to here, and we know that square root of n equals 4.57. 4.57. Okay, so the next step we would want to do is actually, square root of n, so standard deviation. We would divide the standard deviation by that number. So our standard deviation here was 50, so 50 divided by 4.57. Just to speed things up, I've already calculated that. Excuse me. And that gives a standard deviation of 10, sorry, that gives us a standard error of 10.93. So now we have, so far in this equation, we have our numerator. So let's look at our top values here. Let's try to get x minus x bar. That would be 575, or sorry, x bar minus mu. That would be 575 minus 500, which is pretty easy. Should just give us 75. So we get an equation of 75 divided by 10.93. And if we were to actually calculate that out and would round our results, we would get a t-value of 6.8. Now, wow, that is a horrible 8. Hold on a second, let me erase that. That's what I get trying to draw with my right hand on a mouse when I'm left-handed. Let's try this again. We would have got a value of 6.85. So our t-value is 6.85. So not too hard to calculate that. Just got to follow our order of operations, and when we're good to go on it. So step 4 is done. We got our t-value. We calculated our test statistic. So now our final step, we need to compare, decide, and conclude. and basically see is our t-value large enough for us to reject our null hypothesis. And remember, it's large enough if it's bigger than that critical value that we got in step 3. So we got a t-value, or t-test statistic value of 6.85. This is much larger than our critical value of 1.75. So we can safely reject the null hypothesis and conclude that individuals, because this is a one-tailed test, we would conclude that our research hypothesis must be true, and therefore individuals who take the prep course have a significantly higher test average than individuals who do not take the test. See, so basically, I mean, it's very similar to the z-test we talked about, just there's a few minor differences. For the test, you're going to want to be able to calculate both these. So you definitely want to do some of the practice problems in the book and make sure you're ready for this. But okay, this finishes up for this little lecture. We also got some stuff we're going to talk about when it comes to mainly what's called confidence intervals, the stuff that's mainly covered in chapter 7 of your book if you're using the Bachman and Paternoster book. So you might want to take a little break and then come back and watch those, because we're done with this for now. Or go and practice this some would probably be the better bet, and then come back a day or two later and watch the confidence interval video and then practice that separately. Alright, but either way, you guys have a great day. I'll see you in the next video.